Good morning. My name is Jihyun, and he's one of my company fellow named jihyun. And now we prepared a session named Architecting a Managed Kubernetes Service on OpenStack for public service delivery. And I started 3 minutes earlier because I have a lot of things to tell you. So let's start our session. And my team, I prepared my team's experiences and trials and errors while architecting and also on operating. So this is the table of contents of this session. So first, I will introduce about this service named KakaoCloud. And in South Korea, there's the messenger app called KakaoCloud, and it is used by about 100 million people, around 50 million in Korea and another 50 million in global. It's not a huge service, but as you can see that the last yellow thing, that over 94% of the South Korean are using it now. So this means it is a dominant messenger application in this country. Because Kakao already has many users, and many services that launch also quickly gains a large number of users. So, for example, it now has high market share in many areas like banking or webtoons, entertainment, games, and also in finance. All of these services are deeply connected to KakaoTalk, so users can easily access them. So, after building many successful services in Korea, Kakao decided to enter the public cloud market. So in 2023, we officially launched KakaoCloud, starting our services as a cloud service provider. And this is all services from KakaoCloud, and you can see the blue box on the Kubernetes engine team. And now my team developed and operates a managed Kubernetes cloud service. In this talk, I will share the design decisions, challenges, and lessons learned while building and running these services. So first, as a latecomer in CSP market, we have many chances to study other great CSP architectures, and our current focus is to fully migrate all KakaoCloud service to our platform. So we wanted to share these architecture decisions and operational troubleshootings with you because I believe many of you will relate to our experience. So if you have any ideas or suggestions or would like to share your thoughts, just please feel free to us and feel free to me after this session. And then let's start our challenge. When we started designing our Kubernetes service, we had 2 major goals. And the first one is, since the cloud service is a very latecomer, we wanted to learn we wanted to learn best practices of global CSPs. And we studied our providers and architectures and tried to understand how other CSP build managed Kubernetes services. So our goal is to build a fully managed Kubernetes engine with hidden control plane from users. And the second challenge is determined to build Kubernetes cluster with multi-AZ. This second challenge started from one big disaster. In 2022, a data center fire occurred in Korea. At that time, most Kakao services were not built across multi-AZs. So in that day, there were a major data center fire, and nobody expected a full data center burned down completely, and it happened even in a weekend and suddenly. So for 2 days, people couldn't send message with each other even in a weekend, and also our developers and engineers couldn't go home during 5 days. So this was a kind of big wake-up call for everyone. And at the time, we were still building beta version of Kubernetes engine, and the data center fire happened. After that incident, multi-AZ architecture became very essential for every infrastructure component in Kakao Group. So we have to design our architecture can be survive even in a full data center failures. And from now, let me explain from the first challenge. The first thing is hiding control plane from end users. Before I explain how we hide the control plane, I first need to show you the overall data center architecture, because we choose Kubernetes native data center. We would build and operate all data center resources using Kubernetes. The meaning everything in a Kubernetes native way mean using Kubernetes to control not just for application, but also hardware, software, networks, virtual machines, and even Kubernetes itself. And we have just containers and Kubernetes, then we can deploy and manage the same environments anywhere. The third reason is Kubernetes' biggest picture is using a declarative style, and which helps us manage resources more consistently and makes enable to use reconcile logic to all resources. And even if some tools cannot be directly controlled by Kubernetes like OpenStack, you can use it deploy and manage way also. So, but if everything is managed by Kubernetes, then how do we manage Kubernetes itself? The answer is Kubernetes again. To do this, we choose two open source tools. First one is Cluster API, and second one is decouples. Cluster API is a tool that allows you to declaratively manage Kubernetes clusters, including provisioning, upgrading, and operating them. Using this tool means we can manage Kubernetes in a Kubernetes native way. So the second one is the decouples. This helps us deploy Kubernetes onto a bare metal host, which is a physical machines without virtualization. And that means Cluster API works like a plugin and can support many different infrastructure providers. You can see the central box, that's a Kubernetes management cluster, and we can use it easily create a cluster with the management cluster. And internally we call that as a ring 0 cluster. And as you all know, ring 0 is from Linux kernel protectionist, the kernel layer. Similarly, our ring 0 cluster is the most critical part of our infrastructure. So it manages and controls all other clusters, and also itself. So with ring 0 at the core, it provisions the data center with all other Kubernetes cluster in an automated way. And we structured our environment into various types. And you can see the left side, the ring 0 clusters for the core, and the shared cluster for the all shared resources, and the OpenStack controller for managing OpenStack infrastructure. So all together we call it undercloud or underlay cloud. I heard this term is from the Red Hat, similar the idea of overlay and underlay networks. Using this undercloud architecture, we build and manage everything with Kubernetes native resources. And there's a overcloud area named user resource only for user resources. And today's presentation is one of the platform service, our Kubernetes engine. So here is a simplified view of our architecture, showing just the overcloud and undercloud. In the undercloud, we deployed and run the internal Kubernetes engine controllers, and in the overcloud, we provided OpenStack users. So when Kubernetes engine our Kubernetes engine also has a custom cluster API and custom controller, such as external etcd, and also we need custom provider to provision OpenStack infrastructure. And when a user requests create cluster, then undercloud's Kubernetes engine handle it and provision user cluster on overcloud. So the explanation is so long from here, so this is the part I want to highlight in this session. Inside each user cluster, we separate the control plane into a different VPC for a full management. So this means a managed VPC for the control plane and user VPC for the workload nodes. And because of a different VPCs, worker nodes cannot connect to control plane machines. So we solved this problem to enable communication between the control plane and the worker nodes. We set up a dedicated router over there, and one interface is connected to the managed VPC, and other is connected to the user VPC. And from worker to control plane traffic to access the Kube API, the workers use an internal endpoint, and this endpoint is routed to the managed VPC, so it allows Kubernetes access to the Kube API server. And also to hide the control plane from end users, we changed the default Kubernetes bootstrapping flow. So we didn't join control plane machine as a node in the cluster. This is cluster API's basic bootstrapping logic. And when you have a create cluster, first generate coordinate user data, and then second bootstrap virtual machine with a template and Kube API join. After join control plane nodes, then all VM initialized, check control plane node is healthy. This is a basic process. And we customed it to run control plane independently. We need some customized logic, and the first one is the same, but when it the second one, we didn't use Kubernetes, just installed Kubernetes in a standalone mode. So and then instead of checking control plane status through nodes and the third layer, and we check the health of the control plane by directly calling the Kube API server endpoint. So this is the details of bootstrapping template. You can see the bootstrap take Kubernetes and bootstrap post Kubernetes when bootstrapping the VM. And since we don't use kube agent, we have to manually implement all the initialization process that Kubernetes normally performs when joining nodes. So with this architecture, control plane nodes are hidden from end user with separated VPC and with not joined as a control plane node. And we need also hit essential static paths in control plane from users. To achieve this, we separated all cluster management components in isolated container, such as Kube API server, controller manager, and Kube scheduler. So in a worker nodes, even end user runs kubectl get pass all or kubectl get demonstrate all, they cannot see the essential static path. And one of the biggest challenge was figure out how to manage this deployment, how to manage and deploy the static paths and add-on features. So normally in Kubernetes, things like static paths and add-on features like cluster autoscaler and the load balancer controllers are deployed in standard paths, but we use isolated container. So we developed some lightweight agents in a config reloader, and it watches the states of the cluster and helps install and synchronize all components in one cluster. And because all of our clusters run on OpenStack, each control plane VM can access its own OpenStack metadata. And this includes clusters information like networks, image, and machine spec. And the agent reads this metadata and uses it to update and sync to manage all cluster status. Then the agent fetches Helm charts from our internal Helm chart repository and deploy on control plane and the other on worker nodes. This with the entire process, and this could be the control plane still invisible. The second key point we focus on while designing our Kubernetes engine is building a high availability architecture. So I mentioned in chapter 1, after a major incident in 2022, this is a Google map of South Korea, and you can see the several data centers from here. And we operated the data centers, and even if one data center is failure, like back in 2022, the remaining others can continue running the service without interruption. And to further improve more stability, we also decided to separate etcd servers from control plane. This separation gave us two major benefits. First, if the control plane is a failure, it doesn't affect etcd server. Likewise, an etcd failure doesn't take down the control plane. And the second one, you can scale each of them independently. So we can just add more control planes and only can add more etcd. So scale up down is very freely. And let me explain how we designed the overclock layer to support multi-AZ architectures. The control plane managed in managed VPC, and each AZ is connecting through a transit gateway, so the entire network is fully connected and routable. Within each of these AZs, we deploy control plane nodes and etcd servers. And the default setting is 2 control plane machines and 3 etcd servers spread in 3 AZs. And the undercloud is also deployed across multi-AZ with custom controllers. So let's assume a disaster again. And like the incident of years ago, let's assume that one of data center becomes unavailable. And this is actual message logging from our team. And we have conducted a disaster recovery situation every year. And this message on the screen is a real backup log. And in the situation, we assume a fire had broken out in one of our data centers, so all resources and network cannot use. So we actually disconnected network in the situation during the exercise to make the scenario as realistic as possible. From that situation, and each team, like hardware, from hardware to compute to all paths like MySQL or storage team, checks multi-AZ service status and verifies user service recovery. So in Kubernetes engine team, our underlying cluster is already provisioned in multi-AZs. So even if AZ-A is broken, AZ-B is still active. And with that declarative concept of Kubernetes, underlying controller provision resources to active data center automatically. And now, if you're an engineer working in production environments, you might be wondering if control plane and etcd nodes are distributed across 3 AZs, doesn't this increase network latency? So, well, actually we gain high availability, but seems not sacrificing performance. So that's a fair question, and yes, using a multi-AZ architecture does introduce network delays. And about this, while preparing this session, I found some interesting articles. This was a question raised when Google announced plan to build a gaming cloud. And the answer is because of the light of speed is more slower than a fiber in a cable, so only solution is geographic center. So to resolve this, the first approach was at the hardware level. While I cannot go into more detail about the internet network architecture because of company security, so I can say that each AC VPCs are connected through a transit gateway, and we use the highest bandwidth available among our equipment. And in that architecture, we actually measured etcd performance between 3 etcd in a single AZ, also in a multi-AZ, and the result was not noticeable difference in network speed between etcd members even across ACs. And the second approach was at the software level. And this method depends on how end user designs and operates their clusters. And one effective method was using topology-aware hints. It can use other paths to hint your same availability zone. So it can increase the chance that request routing with the same AZ. And this is an optional thing I found. In a large-scale cluster, like more than 300 worker nodes and more than 2,000 services, you can use CNI plugins like Cilium or Calico that replace proxy. The solutions use eBPF instead of IP tables to handle proxying at the kernel level, which improves performance and reduces latency. So so now introduce our actual operational challenges with this architecture. If you ever operated the Kubernetes cluster yourself, or you might be wondering how a few things at this point, and you can wondering how to operate Kubernetes cluster in this architecture. It was also one of our operational challenges. And to make this possible, we designed the cluster upgrade strategy. Since we're using a cluster API, we choose cluster API template pattern. This image below, it shows a Korean winter street snack called bungeoppang, fish-shaped pastry. And you pour ingredients in the mold, and then the fish shapes come out on the right. So in Korea, this is actually a common analogy used to explain object-oriented programming, like class and its instances. So similarly, in our system, clusters are based on predefined templates, just like these molds. So let's see the left side as the for this version 1.32 templates, and then user clusters are created by applying these templates to the user's infrastructure resources. So if you want to upgrade, then you need to change template with new version. Then also with the new template and user data, new versions cluster is created. And it should be zero downtime while upgrading. And so we choose blue-green update logic for cluster upgrades. And it's provision a new BlueStack first, and then switch endpoints or traffic to new BlueStack. And after all endpoints migrate, scale down old green one. And let's see, this is the old version cluster of 1.32. And the control plane has its own etcd endpoint information from Kubernetes server part below the red box. And you all upgrade because the logic is acting from the undercloud Kubernetes engine controller. First, you need to make new versions etcd BlueStack. And the old one is 1.32 and new one is 1.33. And etcd must be created by sequentially and must add with the new members, so it ensures data consistency. Only after confirming that all new etcd nodes are healthy members of that cluster, then we continue with the control plane rolling update. And we update the control plane nodes one at a time to prevent any disruption during the etcd endpoint switching. When the first control plane is updated, the old control plane sends request to the old endpoint, and new control plane sends request to the new etcd endpoint. So during this process, both old and new etcd stats contain the same data consistency, so operate as a healthy kernel set, and this ensures zero downtime through the upgrade. And that's all. Few versions control plane is active. The new control plane is now accessed to new etcd stats, and we don't need anymore the old etcd stats. Then we scale down to remove all the etcd stats before deletion. When there's some etcd member is a leader, then you need to transfer leader election gracefully to avoid breaking the etcd quorum. And this completes the zero downtime upgrade to the new version. And also there are other logic for workload layer and work nodes. And each worker machine is also upgraded by one using the new templates. But that part is outside of this presentation, so maybe possible I will prepare another day. So this is our challenges when you manage your etcd separated from control plane. We faced some operational issues like this, managing etcd. During operation, we found this is pager alert from the etcd controller, and some etcd machines became unhealthy and failed. So first, I started debugging the issue. In the etcd logs, we saw a warning 80% of file descriptors are used. And so we checked the number of TCP socket connection on the etcd server. And I found that too many file descriptors were open in part 2379 that are etcd communication port. And surprisingly, most of them in the right side, most of them were either in a closed state or established state, but not actively being used. So I investigated the root cause from two perspectives. First one is from the etcd client side, and the second one is from the server side. First, this is the logic I created at first for the etcd controller. And it creates new etcd clients every time at first start reconcile. And when using all etcd logic, then close connect before end reconcile. And for to solve issue on the etcd clients, I also debugged the whole etcd client package, the upstream code, and also review the etcd client design guidelines and patterns. And the left side is design principles of the etcd client package to understand how it handles RPC calls. And the right side is the actual etcd client code from upstream to create a new etcd connection with gRPC. So it's a bit long. What I discover is, you can see the first line is actual logic in upstream codes when you use etcd CLI new. Then you can see the last one. Every etcd client is created, they use mutex block and a go routine. And so if you create 1,000 etcd clients, each call one gRPC connection, and it also has a 1,000 mutex block. But my logic creates etcd clients at first, then after use all the logic, then close connection directly. And it can easily happen if you use much etcd connection. So the result is, I didn't fully understand how this etcd gRPC actually works. To resolve this, I created etcd client cache structure to reuse etcd clients to maximize gRPC efficiency. So you can see the left logic. If you have etcd client, then you can get etcd client from the structure cache. So the cache layer is designed with a map structure, so it's managed by cluster. And from the etcd server side, we developed also the TCP handshake using TCP dump, and we found something strange. Even if after the etcd client called close, the server is still receiving TCP packets. But this packet has no data. You can see the flag points and the last one length 0. It means it has no date and no zero pay, and there's a zero payload. So in reality the connection was closed, but in the server only kilobyte packets were constantly sent. And there's also find same issues from etc upstream GitHub. And so for the server side, if any leftover connection remains, we make sure that server closes them periodically. And we also increase the file descriptor limits for the etc service, and that it can safely handle more concurrent and more safety connections. So far, we haven't any file descriptor failures now. And the last chapter is ongoing issues with our homeworks. So we need a custom CNI that enables pod-to-pod communication across different VPCs. And we are preparing CNCF certified Kubernetes compliance after solved issue of custom CNI. And this is all our homeworks to resilience our Kubernetes engine. So this is my old session finished, and I spent maximum 3 minutes time. So I brought my LinkedIn QR code. So if you have any question or you wanna give me some suggestion or advice, just tell me or send me message freely. Thank you so much.
Yeah.